But there's two reasons I would encourage that. One is it encourages you to understand yourself and what you think is important. But then it also sets you up to do what you love to do. I'm Steve Sanford. I'm the CEO at Psionic, and Psionic is a company based on a NASA invention that we are commercializing and using to change the way people navigate. Why did I pursue the commercialization of the technology outside of space exploration? I worked at NASA for 28 years, and of course, I got to do all kinds of different things in aeronautics and space exploration and meet a lot of different people making all kinds of discoveries and inventions and innovations. And it always made me wonder why more companies didn't come to Langley and pick up the inventions and take them out and use them in the economy, the bigger economy. Because we were solving hard problems, we had to come up with ways to do that that had application in all kinds of areas outside of space exploration and aeronautics. And it just, over the course of my career, I kept asking myself why this wasn't happening, why people didn't come to take advantage of the inventions in everything from materials to sensing to lidars, you name it. So that, after I left NASA, I went to work in private industry. I did that for a couple of years and realized I wanted to sort of get back to my roots in engineering. And so that's when I decided to figure out the answer to my question by trying to do it myself. And so I licensed a technology that I knew that had lots of potential, lots of power to change the way things were done, and started Psionic based on that technology.
So my name is Rob Fleschauer. I'm the Senior Vice President for Engineering and Operations here at Psionic. And I've been here since September of 2021. What really was the hook, to be honest with you, is I worked with Steve in the past. So I was managing a contract out at NASA Langley, the Science and Engineering contract, and that's where I got to know him. When I first started, I was the engineering group manager for the contractor company. Steve was the engineering director, and so we sort of developed a relationship there, and he knew, what I was doing, and evidently, he liked what he saw because, a few years ago he came back around to me and asked me to manage the engineering group here. That was my first job here. And so we had that history, and then I knew, this is kind of interesting too. So Diego, our chief engineer, Diego Piratet, he was one of our subcontractors on the contract that I was managing. So I knew Diego as well. And one of the tasks, one of the technical direction notices, task orders that we were working on was the NDL. So I kind of saw that as it was being developed, and I knew Diego and his staff from back then. I also knew Steve, and so when we got this company launched, I was already aware of the navigation Doppler lidar. I knew it was really cool technology, and to be part of that, was very, very appealing to me, as well as working with those guys and the other folks that they'd put together at the time.
My name is Jamie Lane. I'm an optical engineer here at Psionic. I think my motivation, my background, mechanical engineering, and my PhD work was focused in laser spectroscopy and spectroscopy on combustion and plasma-assisted combustion systems. And so that's sort of what drew me to the field of photonics. That got me there from mechanical engineering to photonics. And I think just working on things that are photonic related and that can solve meaningful problems, it's going to address issues that we have and provide a meaningful impact to society.
The origins of the technology lay in the Constellation program. And in that program, which basically said the United States is going to shift from the shuttle-based program with building a space station to going beyond Earth orbit and going back to the moon and to create a permanent base. Well, to have a permanent base, you need to be near water. And the place we knew there was water, based on remote sensing of the moon, was the South Pole. The problem is the South Pole is the hardest place on the moon to land. And so the lighting is terrible. The terrain is really rough and harsh. There's craters and boulders. And half the time you're going to approach from the dark side, all right? Figuring out how to build the sensors to autonomously fly the lander to a very small spot with no boulders, clean spot at the South Pole, was a very difficult problem. And that's what, what our technology was invented to help solve. It's not the only part of that solution, but it's a big part of that solution. So what is it about this that I thought was so important? The device is essentially an interferometer that allows you to measure your speed relative to your target. And this is a measurement that had not been available prior to this work. If you think about how do you know how fast you're going, there's lots of ways to do it, but most of them, they're not fast, they're not accurate, they're not precise. This invention is all of those things. And being able to measure speed and distance, which this technology also does, are sort of fundamental things. Every system needs to know how fast it's going, how far away things are, how fast other things are going relative to them. And especially in the field of autonomy, I knew that these were measurements that were going to be enabling for future autonomous vehicles.
So I think that was a real breakthrough moment when we realized that we could point our beam pointing unit at the ground, and with an initial heading we could navigate really successfully. I'll talk a little bit later about the challenges with that, with navigating, but in essence, when we figured that out, that there were other applications, and especially a really useful one that had a lot of applications, especially for the military. That was a really a breakthrough moment, and something we realized was probably going to have as big or bigger a market than the space units that we were developing.
Sean McCormick, Senior Vice President here at Psionic. Being in the fiber optic world for so many years, we did a PIC development in the past. I had a lot of familiarization with what they're doing, what they want to do, and where they want to go. Transitioning from a space-focused business, which I would call a project business, to more of a product business. So you're less reliant upon project NRE money, less reliant on DoD contracts, budgets, NASA budgets, whereas now you produce a product, and instead of making one that you know is going to go to the moon, you're making thousands that can go into a truck going cross country, into a drone delivering a package, or into a defense platform vehicle in theater, navigating in GPS-denied environments. So it was very, very different, and it was a great opportunity to take this, what I would say, very precise, very high-tech, lunar landing type of technology, and take cost out, take size out, teach them how to make thousands instead of one, and then take it to market and launch it in some place that's what I would say new. Right now, what we're doing a lot of is educational sales. We have to teach people what our LiDAR is.
My name is Amir Reza Mahigir. I am the Director of Integrated Photonics Development at Psionic. Joined Psionic in 2020. It's been a very nice journey so far, very exciting technology that we are developing here. I started in January of 2020. After a couple of months, I guess, maybe 3 months, then we had the pandemic and we were sent home to work from home. We do a lot of experimental work, so working from home was really challenging to us. But it was also an opportunity for us to develop a lot of computational simulations for our lidar systems in order to see how they perform in the virtual domain and see how we can expect and what we can expect to see in our labs. Later, when we went back to the labs, we were actually able to see if we could get those simulations right. We could get good agreement between experiments and those computational analyses. It actually turned out to be a very fruitful period of time that gave us a different opportunity to look into some of the lidar problems and complications in a very different way that's not necessarily lab related.
My fears and misgivings for the process. Of course. Well, I don't know how to do this. Where am I going to get the money? How am I going to get paid? How fast can I learn these things? And or can I find people to help me get the things done that I was not good at based on my previous experience? That was sort of the biggest fear and misgiving I had.
So one of the biggest problems with ground navigation or just navigating in general is you get drift. It's a mathematical problem. It goes through something called an S matrix. You get the velocity vectors, and then you kind of you have three unknowns and in an equation, and you have three solutions you're able to solve for the overall vector, your navigation vector, the direction you want to point in. And so constraining that drift and not having and keeping it so that it doesn't exponentially go off in the wrong direction is really probably the biggest problem with ground navigation. And so we hired a couple of really sharp guys who developed that algorithm. They're developing what we call the navigation filter, which kind of constrains all that. And when we got that figured out and started really seeing some good test results with our ground navigation testing, that's when we knew we were going to be able to solve that problem. It might take us a while, and we've gone through several different instantiations of that, but in the end, that's the key, is getting the filter right.
It gave us a lot of insights in a very short amount of time, an opportunity to see how our ideas can, in a virtual domain, can at least roughly be translated into a real circuit. It gave us a head start, I would say. Instead of going through different multiple design cycles and fabrication cycles for your real chipsets, we kind of took some of that weight away from experimental activities, which takes a lot of time, into simulation and virtual domains, which can be faster. I would say it gave us a good initial velocity.
We knew we had a lot of things to do to take this sensor and make it something that would make an impact in the private sector or the Department of Defense. We had to make it smaller. We had to make it rugged. It was designed for space mission, so it was already pretty rugged, but that also made it expensive and larger. So we had to get it smaller and less expensive, but keep it so that it would live in the environments that, say, the Army would put it through, or even just, to go in a car, for example. That's a pretty tough thermal environment.
It's difficult as a hardware company to communicate what you are and what you can do and how you do it. So funding the first year was definitely a hurdle. As I said earlier, this is now a product. The same product could be deployed on land, sea, air. It could be on a drone. It could be on a vehicle. It could be on a motorcycle. It could be on a bicycle. It could be in a backpack on a dismounted application where somebody's just out walking through the woods, capturing and mapping what the mountainside looks like. So when you start looking at that, now it's looking at environmental conditions, shock and vibration. Vibration on a helicopter is very different than vibration on a vehicle. Temperature. If you're on a plane in the middle of Saudi Arabia, on the tarmac, it's really hot. And the second they take off, it gets really cold. So you have massive changes in temperature. So all of these things you have to be able to compensate for. And the robustness is that, now we're in environments where we get beat up pretty good. So we've learned a little bit more about robustness, and the design has taken a few turns over the past year, few iterations. But I think we're there. I think we're really close with, like I said before, with this close to putting what I believe to be a great product into the industry, something that's not out there, something that nobody else has.
When you have it, small, tiny chipsets, and we are talking like few millimeters by few millimeters in size, you need to have in place a setup that can accommodate light coupling from a bigger structure like a laser into a very tiny chipset. We needed to invest in that. We needed to actually machine a lot of things based on our own designs and likings.
I think scaling and developing for manufacturability has probably been one of the biggest challenges. So taking all the components, conducting the trades, and looking at what our performance requirements are, and trying to balance cost with performance of the components. I think that's been one of the most challenging. And so we're going from essentially the thing the size of a refrigerator initially at NASA down to what our Gen 1 is now, which is about the size of a small shoebox. And so going from that size to reducing the size, weight, power, and cost has been probably one of the most challenging, along with trying to hit project milestones and schedule.
I think the thing that challenges us the most is we know exactly what we need to do to finish these systems. We know that we need these parts. We know that we need to get them qualified. We need to finalize the designs. We need to order parts. It's just in the time. It's the time and the resources, getting the funding and all of those things to be able to buy the parts, to hire the staff, to take us to that next level. It's frustrating at times because we know what we need to do. We know who we need to do it, and we just can't get there quick enough for us. But again, it all comes together. We just keep hammering away at it, and we're making good progress. And this is going to be our year, where we start manufacturing at some volume, both our SurePath ground system, and we're going to finish our design and get it qualified for our space system, our new. And that's exciting for us.
When we built our own navigation filter, that gave us an advantage over everybody else. And, the team that built the nav filter and the team that built the sensor that made that nav filter as good as it is was really, a big accomplishment for us, I think. And it sort of set the stage for the company where we are now.
It's a huge technical challenge, but it's really the thing that's going to make us successful in the end, because we're able to get it small enough and power, a lot less power use, and have the same or better capability. And it also ruggedizes it from using the fiber optic cables and so forth. So that's huge, and we've made a lot of advancements just this year. We've had some good breakthroughs that are allowing us to get that down the road and get that qualified this summer and start putting it in our systems.
I remember we worked really around the clock to take those chipsets that were fresh out of the box, package them with the required electronics, the receiver systems, the electronic system, the carrier boards that we needed to operate those chipsets, because you always need a controller board to operate your ICs. Same for photonic integrated ICs. Took us a while, a few weeks, to have everything packaged and assembled the way that we wanted. And then we saw that in the lab, we could actually do a fully functional navigation solution with different, with multiple lidar channels. and we were able to measure the velocity vectors, all happening on a single photonic chip. That was probably the most exciting moment of my career here at Psionic, when I saw that what we have been working on for the prior 4 years actually got translated into a real technology.
Yeah, you know, the validation of the product has come from some of the demos that we've done. So we were granted almost a $7 million contract from what they call Mantech. Mantech is a rapid manufacturing opportunity within the DoD. And what they do is they fund companies like us to be able to take an early product, something at a TRL or technology readiness level 7 or 8, and get it quickly to a 9. That was a huge validator for us in terms of the Army producing that kind of funding over a short period, 24 months, to get that out there.
So recently we just integrated one of our systems on a NASA FA-18 jet and flew it over Death Valley. So the whole process of taking our NDL technology, integrating it on an aircraft, flying it over Death Valley, and just validating what we sort of already knew, that, you know, what the system was capable of, but seeing it in a real world application. I think that was probably one of the wake-up moments or exciting moments for me as an engineer.
So we've gone, from something that's fairly large and has a lot of mass to something that's probably, I think we've gone from 80 kilograms down to 4 or 5 kilograms, and we're going back down even to 2 or 3 kilograms for mass now. So some pretty significant changes and a lot less power. It's a lot less power hungry than it was before. And so, yeah, we're really excited to get that design out there and get it qualified. We're really excited about the future. We think that we're going to expand and have manufacturing across the United States. We want to be co-located with our major customers, and of course we have to look at supply chain things and where the parts are coming from, and just optimize and create efficiencies wherever we can. So, yeah, the future is very bright. I think we're going to have. We're going to continue to improve the technologies, the sensors that we have. We're going to continue to make them smaller. We're looking at making, our entire system the size of a cell phone or even less, in the near future, even in the next couple of years. And so by 5 years, we think Psionic will be a name like Apple or Microsoft, and we'll be out there, and it'll be really cool to have been part of that.
Not only excitement, but also a feeling of, okay, we achieved something that's groundbreaking. You will feel proud at that point, because that technology, which is something that I had the opportunity to be part of, now can help a lot of people in different areas, from space exploration to helping military vehicles, to helping cars and drones. You'll see the impact out there, and it makes you feel proud. But also throughout the process, I had the opportunity to work with so many different people here at Psionic. A lot of them very talented and skilled young researchers, young engineers, fresh out of school. And when you see that, they come here with a lot of excitement and enthusiasm. And that enthusiasm and excitement is put into hours of work. And after a couple of years, when they saw the moment, when I see the happiness in their face, when they see that the technology that they have been working on is actually working, and it's actually a very a technology that we are using in the bigger scheme of things for our navigation solution. When I see that in their face, when I see that enthusiasm being translated into a real outcome, that makes me proud as well.
I think I've always knew, in starting with Psionic, and I knew the potential of the technology. One of the reasons why I came to Psionic, just looking at the potential to make a positive impact on society. You know, as people, our time is a non-renewable resource, and we want to work on meaningful projects. And that's how I viewed this. You know, with the SurePath technology, it's a meaningful solution to solve problems that we face.
I think at the early stages, we were young and needed help. But now we've become like an adolescent where we're getting close to being on our own. We're getting ready to like go to college and be an adult and be able to make our own money. And that's, I think, the biggest transition I've seen over the time here is more of a willingness and an understanding of what we need to do to become who we want to be.
So my advice to NASA engineers who are transitioning with disruptive technologies is I hope you'll stay in the game and come work for a company like Psionic, continue to develop that technology, continue to be part of it. Whether they want to work part-time or work full-time for a few more years, we can definitely use their skills, their genius, their ingenuity. And we have several here, and they are just fantastic staff, fantastic engineers. They obviously think outside the box. That's the reason they got hired in the first place. And we hope that they'll, to continue to work with companies like us and continue to make it great for commercial use.
So one thing I would, encourage young innovators to do is to look at the world and find out what needs to be fixed, what needs to be improved or done better or torn down and rebuilt even. Because it's, the old saying, necessity is the mother of invention is true, but there's two reasons I would encourage that. One is it encourages you to understand yourself and what you think is important, but then it also sets you up to do what you love to do. And when you have a good problem and it's a problem that you really feel strongly that needs to be solved, then you'll innovate and you'll be happy doing your work, whatever that work turns out to be.